This outcome is all about things that swing, bounce, and vibrate. We'll build up simple harmonic motion from its defining rule, track how energy shifts as an object oscillates, and then look at resonance and damping, ideas that matter enormously to real engineering. Let's begin. So what does an oscillation actually mean? It's any repeated to and fro motion about a fixed point, and that fixed point is the equilibrium, or rest, position. Think of a mass bobbing on a spring, a pendulum swinging, or a guitar string vibrating. One complete there and back movement is called a cycle. The time for one cycle is the period, in seconds, and the number of cycles every second is the frequency, in hertz. Let's line up the vocabulary we'll use. Displacement is the distance and direction from equilibrium, in meters. Amplitude is the biggest displacement the object reaches. The period is the time for one full oscillation, and it equals 1 over the frequency. The frequency is the number of oscillations per second, in hertz, which is 1 over the period. And angular frequency, omega, is the rate of phase change equal to 2 pi times the frequency, or 2 pi over the period, in radians per second. Here's the heart of the whole topic, the strict condition that defines simple harmonic motion. The acceleration equals minus omega squared times the displacement. So the acceleration is proportional to how far the object is from equilibrium, and that minus sign is doing real work. It means the acceleration always points back towards equilibrium. That restoring effect is exactly why the motion keeps repeating. When the displacement is 0, the acceleration is 0. And when the displacement is at the amplitude, the acceleration is greatest. Any system that obeys this rule oscillates with simple harmonic motion. Where does that condition come from in practice? Take a spring, which obeys Hooke's law. The restoring force is minus k times the displacement, where k is the stiffness. Newton's second law says force is mass times acceleration. So mass times acceleration equals minus k times displacement. Rearranging, the acceleration is minus k over m times the displacement, and that's precisely the form, a equals minus omega squared x. Comparing the two, omega squared equals k over m for a mass on a spring. So a spring naturally produces simple harmonic motion, and the stiffer the spring, the larger omega, and the faster it oscillates. There's a lovely geometric way to see where the sines and cosines come from. Simple harmonic motion is really the shadow or projection of steady circular motion. Imagine a point going round a circle of radius a at angular speed omega. Its horizontal position is at times the cosine of open bracket omega t plus epsilon, and that is exactly the displacement equation for simple harmonic motion. The quantity omega t plus epsilon is called the phase of the motion, and this circle model is why sine and cosine describe oscillations so perfectly. So let's look properly at that displacement equation. The displacement varies with time, as x equals a times the cosine of open bracket omega t plus epsilon. Here a is the amplitude, omega the angular frequency, and epsilon the phase constant. If the object starts at maximum displacement, then epsilon is 0, and it's simply a times the cosine of omega t. If instead it starts at equilibrium moving in the positive direction, you use a times the sine of omega t. Sine and cosine differ only by a phase shift of pi over 2 radians, and either way, the graph of displacement against time is a smooth wave with amplitude a. Differentiating the displacement gives us velocity and acceleration. Differentiate once, and the velocity is minus a omega times the sine of open bracket omega t plus epsilon. Differentiate again, and the acceleration is minus a omega squared times the cosine of that same bracket, which is just minus omega squared times the displacement, our defining condition reappearing. The maximum speed is a times omega, and it happens at equilibrium where the displacement is zero. The maximum acceleration is a times omega squared, and it happens at the extremes where the displacement equals the amplitude. So velocity is zero at the ends and greatest in the middle, while acceleration is the other way round, and the velocity actually leads the displacement by a quarter of a cycle. Let's put that into practice. An object performs simple harmonic motion with an amplitude of 0.05 meters and a frequency of 2.0 hertz, and we want the maximum speed and the maximum acceleration. First, the angular frequency. Omega equals 2 pi times the frequency, 2 pi times 2.0, which is 12.57 radians per second. The maximum speed is amplitude times omega, 0.05 times 12.57, giving 0.63 meters per second. The maximum acceleration is amplitude times omega squared, 0.05 times 12.57 squared, that's 0.05 times 157.9, which comes to about 7.9 meters per second squared. Sometimes you want the speed, not at the ends or the middle, but at some general point in the cycle. The result for that is V equals plus or minus omega times the square root of open bracket amplitude squared minus displacement squared. When the displacement is zero, this gives plus or minus omega times the amplitude, the maximum speed as expected. When the displacement equals the amplitude, the square root is zero, so the speed is zero. The plus or minus reminds us the object passes each point traveling in both directions, and handily, this equation doesn't need you to know the time. Let's use it. A mass oscillates with amplitude 0.10 meters and angular frequency 5.0 radians per second, and we want its speed when the displacement is 0.06 meters. Start with V equals plus or minus omega times the square root of amplitude squared minus displacement squared. The amplitude squared minus the displacement squared is 0.10 squared minus 0.06 squared, which is 0.0100 minus 0.0036, giving 0.0064 square meters. The square root of that is 0.080 meters, so the speed is 5.0 times 0.080, which is 0.40 meters per second, and it could be moving either way. How do you decide whether to reach for sine or cosine? It comes down to where the motion starts. If the object begins at maximum displacement, use A times the cosine of omega t. The velocity starts at zero, and the phase constant epsilon is zero. Think of a mass released from a stretched spring. If instead the object starts at equilibrium, use A times the sine of omega t. The velocity starts at its maximum value of A times omega, and that's equivalent to a phase constant of minus pi over 2. Think of a pendulum given a push from its rest position. Let's tidy up the idea of phase. The phase tells you how far through a cycle the motion has got, and the full phase angle is omega t plus epsilon, measured in radians. Phase difference compares two oscillations of the same frequency. If they're in phase, the difference is zero and they move together. And if they're in antiphase, the difference is pi radians and they move in exactly opposite directions. And remember, within a single oscillation, the velocity runs a quarter cycle, pi over 2 ahead of the displacement. Time for a quick check. Can you state the defining condition for simple harmonic motion? Where in the cycle is the speed greatest, and where does it fall to zero? How are angular frequency and frequency related? And why does the acceleration equation carry that all-important minus sign? Have a think before we carry on. Let's apply the theory to a real system, a mass on a spring. A mass m on a spring of stiffness k oscillates with simple harmonic motion, and since omega squared is k over m, and the period is 2 pi over omega, the period works out as 2 pi times the square root of m over k. So a larger mass gives a longer, slower oscillation, while a stiffer spring gives a shorter one. Notice something important. The period doesn't depend on the amplitude at all, and that independence is a hallmark of simple harmonic motion. Let's calculate one. A mass of 0.20 kilograms is attached to a spring of stiffness 80 newtons per meter, and we want the period. Using the period equals 2 pi times the square root of m over k. First work out m over k, 0.20 divided by 80, which is 0.0025 square seconds. The square root of that is 0.050 seconds. Multiply by 2 pi, and the period is about 0.31 seconds, which corresponds to a frequency of roughly 3.2 Hz. The other classic oscillator is the simple pendulum, a small mass on a light string of length L. It swings with simple harmonic motion, but only for small angles, roughly under 10 degrees. Its period is 2 pi times the square root of L over g, where g is the gravitational field strength. Notice the period depends on the length and on g, but not on the mass or the amplitude, so a longer pendulum swings more slowly. That reliability is exactly why pendulums have long been used to keep time. Let's find the length of a pendulum with a 2-second period, taking g as 9.81 meters per second squared. Rearranging the period formula, the length equals g times the quantity, period over 2 pi, all squared. The period over 2 pi is 2.0 divided by 6.283, which is 0.3183 seconds. Squaring that gives 0.1013 square seconds. Multiply by 9.81, and the length comes to 0.99 meters, so just under a meter. Now let's think about energy as the object oscillates, because it's constantly swapping between two forms. The kinetic energy, a half times mass times velocity squared, is greatest at equilibrium where the speed is highest. The potential energy, a half times k times displacement squared, which is also a half times mass, times omega squared times displacement squared, is greatest at the extremes. The total energy stays constant, equal to a half times mass times omega squared times amplitude squared, or a half times k times amplitude squared, so it's proportional to the amplitude squared. Ignoring friction, energy just shuttles back and forth between kinetic and potential. Let's put figures to that. A 0.30 kilogram mass oscillates with amplitude 0.040 meters and angular frequency 10 radians per second. And we want the total energy and the maximum speed. The total energy is a half times mass times omega squared times amplitude squared, so a half times 0.30 times 10 squared times 0.040 squared. Now, omega squared times amplitude squared is 100 times 0.0016, which is 0.16. So the energy is a half times 0.30 times 0.16, which is 0.024 joules. The maximum speed is amplitude times omega, 0.040 times 10, giving 0.40 meters per second. And you can check that a half times mass times that speed squared gives the same 0.024 joules. It helps to picture the energy at the two ends of the motion. At equilibrium, where the displacement is zero, the speed is at its maximum of a times omega, so the kinetic energy is greatest and the potential energy is zero. All the energy is kinetic. At the extremes, where the displacement equals the amplitude, the speed drops to zero, so the kinetic energy is zero, and the potential energy is at its greatest. All the energy is potential. The oscillation is just a continual trade between those two. Now let's distinguish free from forced oscillations. A free oscillation is what happens when you displace a system and simply let go. It then vibrates at its own natural frequency, which we write as F0. A forced oscillation is different. There you apply a periodic driving force, and the system is made to vibrate at the driving frequency instead. Pushing a child on a swing at regular intervals is the everyday picture, and the crucial fact is that the response is largest when the driving frequency sits close to the natural frequency. That brings us to resonance. Resonance happens when the driving frequency equals the natural frequency. At that point, energy is transferred most efficiently into the system, so the amplitude grows large. Sometimes that's exactly what we want. Tuning a radio picks out one station's frequency, and musical instruments amplify particular notes. But sometimes it's dangerous. Bridges and buildings can be shaken alarmingly, which is why engineers deliberately design structures so their natural frequencies avoid the frequencies likely to drive them. It's worth seeing resonance as both friend and foe. On the helpful side, radio tuning circuits select a single frequency. Musical instruments amplify chosen notes, microwave ovens excite water molecules, and MRI scanners rely on nuclear resonance. On the dangerous side, bridges can be shaken by wind or by marching feet. Tall buildings can sway in earthquakes, and machinery can vibrate badly at its running speed. The engineer's answer is to add damping or to shift the natural frequency out of harm's way, which leads us neatly to damping, the loss of oscillation energy, usually to friction or drag. With damping, the amplitude of a free oscillation gradually dies away over time. Light damping means the amplitude falls slowly over many cycles, whereas heavy or over damping means the system creeps back to rest very slowly without oscillating at all. Damping also cuts down the peak amplitude at resonance, and this removal of energy is exactly how unwanted vibrations are brought under control. There's one particularly useful case, critical damping, which returns a system to rest in the shortest possible time without any oscillation. It's the boundary between light damping and overdamping. Vehicle suspension uses dampers, the shock absorbers, working near this condition, which is what stops a car bouncing up and down repeatedly after a bump. The same idea makes the needle of an analog meter settle quickly rather than swinging, and door closers use it to shut a door smoothly instead of slamming. Let's collect the key terms from the second half. The natural frequency, EF0, is the frequency at which a system oscillates freely. A forced oscillation is one driven by an external periodic force. Resonance is the large amplitude response you get when the driving frequency is close to the natural frequency. Damping is the reduction of amplitude through energy loss, and critical damping is the fastest possible return to equilibrium without any oscillation. One last check before we finish. How does the period of a simple pendulum depend on its length? Can you explain the difference between a free and a forced oscillation? Under exactly what condition does resonance occur? And why is critical damping the right choice for a vehicle's suspension? Those four will tell you how well it's all settled in.